In Part 8 of the Unit 9 notes, we are going to be covering empirical formulas. Empirical formulas. The formula with the smallest whole number mole ratio of the elements. The empirical formula might or might not be the same as the molecular formula. To solve for the empirical formula, when given percentages, you can assume 100 grams to find the mass of each element. Then you will convert from mass to moles for each of the elements within the compound. You will divide each mole value by the smallest mole value. If all the mole values at this point are whole numbers, these values will become the subscripts. If one or more of the mole values are not whole numbers, you will multiply each number in the ratio by the smallest number that yields a ratio of whole numbers. This will usually be a 2 or a 3. You will see examples of each of these steps within the next couple of checkpoint questions. For our first question, a compound is analyzed and found to contain 25.9% nitrogen and 74.1% oxygen. What is the empirical formula of that compound? So the first thing I'm going to do is list out each of my elements. So I know there is a nitrogen and I know there is oxygen. 25.9. One of the steps on the previous slide said to assume 100 grams. So if I had 25.9% of 100 grams, that would be 25.9 grams. And if I had 74.1% of 100 grams, that would just be 74.1 grams. So there's actually no math involved within this step. You're really just switching out one unit for another, one that you can actually then use to convert to moles, which is our next step. All right, so next, I am going to do a one-step gram to mole conversion. Grams of nitrogen on the bottom, moles of nitrogen on the top. And the mass I am going to get from the periodic table. So the molar mass of a nitrogen atom is 14.01. I'm going to do the same exact thing for my oxygen. Grams to moles, 1 mole. The molar mass of an oxygen is 16.00. Now, sometimes students get a little confused at this point because they're thinking to themselves, well, nitrogen and oxygen are both diatomic elements. So why do I not double the mass here? Well, both of these elements are currently within a compound. So the rule of diatomics is not going to apply in this situation. So we are going to just consider a single atom, or in this case, a single mole of that atom. All right, from here, I am going to divide across. I have 1.85 moles of nitrogen. And for the oxygen, I have 4.63 moles. Now, neither of these are whole numbers, and you'll pretty much never have a situation where these will be exactly whole numbers at this point. So what we're going to do is divide both of these values by whichever one was smaller, which is going to be our 1.85. Now, for the nitrogen, that's going to come out to a nice whole number. It's going to be 1. So now I have 1 mole of nitrogen. For the oxygen, it's not quite so nice. It comes out to about 2.50. Now, if I were to use this for the empirical formula, my formula would be NO 2.5. And I know that I'm not allowed to have a subscript, which is a fraction or a decimal. So next, what I'm going to do, I can multiply both of these numbers by 2. If I multiply this by 2, it will equal 2. If I multiply this by 2, it will equal 5. Now I can use that as my subscript. So the nitrogen is going to be the 2. The oxygen is going to be the 5. So this is the same exact ratio as what I have up here, but now it's in a whole number form. So this is my empirical formula. For our next question, we have iron and we have oxygen. The mass of oxygen here, they said that we had 69.94%. So again, I'm just going to assume 100 grams, which means that's how many grams I would have. The oxygen is going to be 30.06 grams. Going to do a one-step conversion to moles. Grams on the bottom, moles on top. The molar mass of iron is 55.85. Grams to moles. For oxygen, it is 16.00. For my iron, I have 1.252 moles. And for my oxygen, I have 1.879. I'm going to divide both of these by whichever number is smaller, which is the 1.252. So that leads to 1 mole of the iron. And for my oxygen, that comes out to 1.5. So this is a similar situation to the previous example. My formula appears to be FeO 1.5, but I know I can't leave it like this. I'm going to do the same thing I did before. I'm going to multiply both of these numbers by 2. That's going to give me a formula of Fe2O, and 1.5 times 2 is going to be 3. So that gives me a whole number ratio I can actually use. That's my empirical formula for this one. In our next example, this one is a little different just because I have 3 elements instead of 2. So I'm going to be breaking this down into carbon, hydrogen, and oxygen. For the carbon, I have 48.64, and I'm going to use grams instead of percent. For the hydrogen, I have 8.16. For the oxygen, I have 43.20. For each of these, I'm going to do a one-step gram to mole conversion. So grams to moles, the molar mass of carbon is 12.01. Grams to moles, hydrogen is 1.01. Grams to moles, oxygen is 16.00. So I'm going to figure out how many moles I have for each of these. For the carbon, this comes out to 4.050. For the hydrogen, this is going to come out to 8.08. And then for the oxygen, this comes out to 2.7. And for this one, actually, if I was keeping with the significant figures, this one has 4 significant figures, so I'm going to add on a couple of zeros here. So 2.700. All right, so out of these 3 values, the 2.7 value is the smallest. So I'm going to divide each of these by that. It means I'm going to have 1 mole of the oxygen. For the hydrogen, it's going to come out to 3. And for the carbon, that comes out to about 1.5. So my formula would be C 1.5 H3O. But just like in the previous 2 problems, I cannot have a 0.5 here. So I'm going to double each of these so that they're a whole number ratio. That leads me with C3H6O2. So that would be our empirical formula. That concludes part 8 of our Unit 9 notes. In part 9, our final part, we are going to be covering how to determine the molecular formula.